Okay, so we're in part 2.1. Okay, so we separated small parts so you can be able to study in an effective way instead of listening to a very, very long lecture. It's better to break them into parts. Okay, so now we get into equipment life cycle failure rate. So when we say equipment here, it can be a small part of the system, or it can also be equipment. Okay, so it means just component. You try to understand as a component, in the system. And again, component, they have their own life, and the system also have an overall life. And since we use this word equipment life cycle, students usually see this as a tool, okay, and they see it's like a machine life cycle. You can also see that way, but you also have to understand you're studying a system and the component of that system. Okay, we also call that component or equipment. Yeah, so don't just think about like a screwdriver or something, and not that kind of equipment. Okay, but you can also think that you can think like a car. You can think like component of the car. You can also think like your computer. You can think like the motherboard of the computer or a piece of chip. Okay, they all have different equipment life. Yeah. Okay, in general, we call any kind of machine equipment anyway, or system, or parts. So failure happens at different rates during the life of the product. Okay, so infant mortality, because of this word product, don't think like the end product kind of thing either, because even the system, the component of the system, they are actually manufactured part, yeah, from coming out from manufacturing production system. So that's why the way that we use it sometimes confuses you. So don't think like is it equipment like a cell phone or not like that. We're dealing with maintenance of a system, okay, at a production system. So make sure you get that in your head. You're dealing with the industrial maintenance, not the maintenance of the little equipment, okay? Alright, so infant mortality is just a word. It is trying to tell you the first stage of your equipment life, right? Since we're dealing with the life, we go with the time. And here is the rate, okay, failure rate. Now we're looking at the different rates during the life of that equipment. So infant mortality is a debugging stage, okay? That's your first stage. So what we do here is because of the like installation is not good, or the improper design of the system or the component, okay, all the equipment is no good. So it's kind of like a trial stage, right, in the equipment life, and we call that infant mortality, because the system can go wrong if your installation isn't right, okay? The system can go wrong if you have a defective components, yeah, in your product. So chance failure is a second stage. So that's a near constant rate because you're using your equipment and it's functioning, yeah, functioning. So and it's also good for preventive, also predictive maintenance planning. So we study equipment life and second stage heavily, okay? And you do have a chance of failure in this period, okay? That's why we call that a chance failure. But then if you think about the rate, okay, you usually get rate mean the failure rate. That's what we're studying anyway. You usually get a constant rate, so the prediction is accurate, okay? Because of this little scene, like how it can be like a plateau that you can see. So here is like the first stage is like trial, debugging, so it go down. The wear out phase is like going the third stage and the line going up like that. Okay, so that's the final stage of your equipment life cycle, because it go up because since the equipment is kind of old, okay, it's worn out, we call it the wear out phase, the failure rate is going to increase. Okay, the news of the failure rate is not that much, right? You haven't started the system yet, so it's usually go down. So if you look at it, it looks like a butt top right here, so therefore we call that, okay, the equipment life as a butt top, right, term or time or equipment life. A graph looks like this kind of shape. Okay, so that's with the equipment life cycle failure rate. Again, do not forget we're dealing with the failure rate. Okay, going down, not so much failure. Going up at the end of the life, usually stable during the life. If you get it, I'm quite okay. And pay attention to the term, because they use a heavy term right there. Alright, next one. Failure versus time curve. So we're dealing with failure mechanical, failure electrical, failure software. And they all produce different graph. Okay, and we call them curve. And we are studying the failure, okay, against time. Yeah, so this is all time axis right there, and failure is on y-axis. Those who forget about the y and x-axis, so this is y-axis, and this one is your x-axis. Some of the high school, they don't teach you. Some of them is going to teach you. So I'm just trying to review that for you. That's your y-axis, and that's your x-axis, okay? So we call it A, X, I, S. This one is also AX, and then I, S, y-axis and x-axis. Mechanical, electrical, and software. We're looking at the failure. Mechanical go up as time goes on. Electrical going up, down, and then up as time goes on. Software, okay, going down as time goes on. Now I'm going to erase this. Let's go to the second graph right here. So this is just showing you the components. In the system, we have injector, turbo, belts, pistons, and rings, and we have block, and then crank, and then the main, okay, racks right there. So we're dealing with the equipment life, okay, curve. So you're seeing like a buttock. So going down in the debugging stage, stable, okay, for each one of them. It's the same thing. This is the second one, the third one, both, and then the last, okay. So that's a 1,000 hours all the way to our overall. So injectors, okay, shorter life, turbo, longer, and then so on, yeah. So you can see like all of the components, they have different equipment life, yeah. Exponential and probability distribution. So here you can see the percent failure. Percent failure is nothing but you are presenting the failure in percentage. Okay, we have constant going up, increasing, going that way and up, decreasing, going that way and then down. And again, we're studying the failure against time. So this is, you don't have to worry too much about it. All you have to pay attention is a distribution curve. Okay, look like that. Then they look like this. And we have different, these are the application. We call this statistical, okay, distribution. They look different. This is your wave, this is exponential, that's your log normal, base E, and then this is your normal curve, okay? So they look a different slope right there. And in these little dots are your data points, okay? And what's important about the equipment life is that we can use, the second stage to come up with the preventive maintenance, program, because we can use that because it's usually, that phase or the stage rate is usually constant, okay, and they follows a random pattern, and this is just a statistic, it's a data expression, okay, so therefore you can use it for your benefit for predictions. So the most important thing is the second stage for equipment life is useful for preventive maintenance and predictive maintenance predictions. Okay, why can we do the prediction? Because the phase is constant. Because the equipment life follows a random pattern. Okay. Okay, so how do we do the prediction of your equipment failure? So first we study the equipment life in different curves, okay, and we come up with the period that we can use to study the equipment so that we can be able to protect the equipment by doing maintenance. So now we know when to do the equipment failure study and how do we do it. Okay, so statistically we're dealing with the data. So you have to collect the data or the activities of that equipment. So we start to study the equipment in order for us to be able to understand how it can fail. Yeah. So therefore we will test it, we will research it, we will simulate it, and we'll put conditions to come up with the failure data. When will this equipment or components of this equipment fail? Okay. So that's come from testing it, yeah. So I have my equipment ID, I ID my equipment that way, and then I study the equipment. What am I studying? When it will fail, okay, when it won't function. So I get my hours, so after 10 hours, this thing is going to fail, okay, and so on and so on. So this is what we call research, and this is what we call the data, and collecting it and organizing, okay, collected data into a column by using an application is called data collection, it's called grouping, and it's called data analysis. Okay, so we group into the homogeneous group. Grouping is nothing but putting the data into an organized table like this, put the equipment ID, number, hours from your research or test, and then cumulative number of failure. You count how many times this happened, and then cumulative percent, okay, number got to change into percentage so we can understand, all right, the probability, so we can predict to prevent it. Yeah, so that's, we call this a data treatment, collection, grouping, and treatment. So data collection, the data are collected, okay, for each group. If you don't collect this, all it's going to be blank under all of these columns. So now my columns group have data because I collect them and then organize them, okay, and enter the data into the appropriate group like that. And then we're going to look at that data and analyze it. Since you put that way, you can clearly see what's going on. First, I can, see the hours going up according to this ID. I can see the cumulative number of failure going up according to this equipment ID. And I can see the percentages going up according to that ID. Yeah, so that's what's important for the data organization, grouping, collection, so that you can analyze very clearly. So calculate the cumulative frequency, and then we get the percentage. Yeah, frequency is nothing but how many times this thing happened. Percentage is what is the percentage that those things happen, so you can predict. Okay. Cumulative, ongoing percent failure. So the cumulative percent failure column, okay, group in that table is going to keep track of the total failed units. as a percentage of the total units tested. So when you translate that into mathematical expression, that's what we get. So cumulative percent failure, how do we calculate it? Well, we have a fraction right there. It's cumulative number of failures divided by total number of the test units times 100, okay? You usually time your value with 100 to get percentage. So after the failure of the first unit, one of the 10 units being tested. So remember the previous table, and you have equipment ID, okay, and there are 10 of them. So 1 divided by 10 units times 100 is going to give you 10%. So that's a very first row, if you remember, okay, data that we're analyzing. Yeah. So in the first row, you have 1 cumulative number of failure divided by 10 units times 100 is going to give you 10%. Now, exponential probability graph for constant failure rate. So usually the graph looks like this, and this is an exponent because you see the data, and then you see how the lines go up, all right, continuously in a straight line up. So that's a exponential graph. Here we are studying the percent failure against time, so hours of operation of your equipment or system. And the hours of operation is nothing but representing the age, okay, at failure in hours, the same thing. Because you're seeing like at which, okay, hour the system is going to fail. So here looking at the percent failure units. So in exponential probability graph for constant, again, failure rate, constant. That's why you're seeing an exponential graph right there. The reliability was defined as the absence of failure, okay? That's why we represent the reliability is equal to 1 minus failure. 1 minus failure is your reliability. So reliability is the absence of is expressed minus, okay, failure from the whole, which is 1. 1 is presence. So 1 minus, get rid of failure and you will get the reliability. So that's what it's saying. Defined as the absence of failure, then 30% failure. So therefore, if you have a 30%, okay, failure, you're going to take 30% out. In decimal, we write 0.30, and you're going to get 0.70, okay? So in decimal, 0.70, reliability is 70% reliability, okay, in percentage. So that's what it's saying. So that 30% failure would translate to 70% reliability by taking off from 1, okay? Because your system, you have 2 parts, reliable part and failing part, okay? And that is what we call system. Same as you, okay, good, when you're good, and when you're bad, okay, and that's your system. Sometimes you can be 100% good and 0% bad. Sometimes you can be 20% good and 80% bad, right? Same as that. I have a system. That system is 70% reliable, but it can fail 30%. Okay, so that's what I'm telling you all about. And I want you to understand that. Okay, so let's erase this. So every time you take a look at this graph, even if it's giving you percent failure, you know, okay, how reliable the system is by calculating that way. So if you see 60% failure, that means your system is only 40%, okay, reliable. Yeah. So 60%, your system is 40% reliable because your system hours of operation has already run about 49. Sorry, this is 60, so 50, okay, 59% of it. So meaning like 59 hours you run and you have only 60% failure with a 40% reliability. If you run, this system about 59 hours. Yeah. So you will have to run this system every 20 hours. So if you run every 20 hours, you will be getting less than 30%. So that's about 22. So if you go this way, right? So that's about a 22% failure. So you have 78% reliability. So you will run your system 20 hours and then stop. Okay, let the system rest. And then run again next 20 hours. So you can maintain your system reliability at 78%, right? Relatively. So that's how we calculate. Yeah, okay. So let's go to the next one. So data analysis. So here, an exponential probability, again, it is exponential, but when you look at the graph, you see that's going straight up. And you have see there's a little data point right there. If you pay attention, see the little small, and we already checked the y-axis, and we're dealing with the failure again in percentage. And then we have operation hours right there. And in other words, it's the age, okay, at failure, operation hours. You're running the system that many hours, okay? So here is the mean time before failure. So here, mean time before failure, right here in this graph is about 60 hours. So meaning like you can run 60 hours of operation for that system, and your system will fail after that, okay? So you want to stop before that. Yeah. Okay, you don't want to go all over and get a failure right there. So anyways, an expression for a constant failure rate. So MTBF, mean time between failure, line is right here, and graph is right there. They intercept right here, approximately 63.2%. From the computer, my eyeballing is about 60% right there. So anyways, a 63.2% failure. Okay, because we're studying failure anyway. So when you look at this line, okay, we're running about 60 hours of operation. You will have about 63, okay, 0.2% failure. So therefore, 1 minus 63.2% failure is going to give you the reliability of that system. Okay, so not a 50% failure as in normal graph. Yeah. So normally, this is just knowledge. So normal graph looks like this. It doesn't look like that. This is exponential graph. Okay, so if you translate the same data to a normal graph, you will get like that. At that time, okay, you're gonna have like about 50% failure. For exponential graph, we have about 63.2% failure. So if you take this out from 100%, that's your reliability of that system. So you have like, if you calculate, so 100 minus 63.2% will give you about 36.8, okay? Reliability is very low, so you don't want to run up to 60 hours. You want to keep it before that. And if you look at the normal graph, this is your normal graph, and they usually have a shape like that, bell shape, and it's different from the exponential graph right there. Okay, so 50% failure is going to give you 50% reliability, right? Short to the point, simple. But they're just numbers, prediction, okay? Numbers that we use in calculation. In real life, a lot of things can happen, okay? A lot of things can happen because you're dealing with the real people. People have emotion. People are just crazy sometimes. You're going to understand how difficult it is to put the people in a system. You have to use all kinds of management technique, okay, to keep the people working in the way you want them to do it. And that costs a lot of technique, okay, interpersonal skill to do it. Some people are really good. We call them the people person, those who butter up other person and make other people feel good. So when the people feel good, they do what you tell them to do. When other people don't feel good, they don't do. So different management. Okay, there are management who control you by fear, like threatening you with your job and all kinds of stuff, and then make you work, okay, in the line. So anyways, many different kinds of management, and they want to use a different kinds of analyzing graph like that, okay. And usually they go with the exponent because it's more precise. But normally we go with just the normal data because this is something that you usually get, okay, from any kind of data set. This needs a little more calculation, but it's more precise. Okay, so let's get into MTBF calculation again. We already know, right? The MTBF is a reciprocal of your failure rate. We know how to get the failure rate. Just a recall. Review right there. So number of failures divided by number of item hour tested. So 10. Here you have already calculated the number of item hour tested. So that's a 10, 16. And you don't have to calculate in the first example. For the first example, if you remember, your item times the tested hour 1535, right? And so and so. And then you have 7 units and you each unit. So that's one way to calculate. This one is already calculated for you. So all you have to do is just go in there and get it out from your table, right? Already calculated table. So make sure you understand there are two different ways of calculating the failure rate using the same equation, okay? I show you the first method and I'm showing you the second method, which has already been calculated. The first method is you have to calculate it by yourself to get this number, and then you do the same thing and you ended up getting 0.150 failures per hour for the failure rate. Reciprocate it, so you're going to get 1 divided by lambda, and you will get the mean time between, alright, failure, ended up with 66.6700 hours. So this is calculation. Okay, the other one is 63.2% is a graphical estimate, the one that we use a graph, yeah, by eyeballing, drawing on the graph will give you about 63.2. By calculating precisely by using the value will give you about 66.67. So plus or minus standard deviation about 3, yeah. So decision making. We use data to make decision. The best management is a management who don't use emotion to make a decision. And you cannot use your opinion, ideas, what you feel, how you think to make a decision in any of the business, okay? And if you do make the decision of what you think, because what you think may or may not be right, okay? So therefore you don't want to take risk to make important decision. So stay away from how you feel, okay? And get the result data and then analyze the data, repeat the process, and then decide. Okay, that's the way you should be making any type of decision. Okay, so in our case, in this subject, we're learning industrial maintenance, and here we're studying the equipment life, failure, reliability. Okay, and estimated, okay, mean time between failures, and whether we're going to let the equipment fail, okay, let it run, operate, whatever, and then we're going to fix after the equipment failed, or we're going to replace before, okay, the equipment failed, or we're going to run, okay, only the limited number of operation hours and make sure the equipment never fails, okay? So those are the decisions that you have to do. And you will calculate the cost, you will calculate the time, okay? And you will calculate all of that to make that decision. One, let the equipment fail. We're not going to maintain. We're going to just keep on going the operation and make this money, okay? Since you get the constant operation running, producing products, selling the product, getting the profit, we're going to use some of this, okay, money to fix the component when it fails. Okay, that's one way. So it also depends on your system. And if your system allows to do that, by all means, go ahead and do it that way. Decision 2 is you're going to perform a preventive maintenance when we won't let the equipment fail or system fail or any part of the equipment fail. Okay, and we're going to play with the operation hours. So we're going to run only 65 hours because we already knew it is going to fail at 66.67, all right, hours. But if you are a better management, so this textbook did not cover, this is coming from the precise calculation, right? You also have eyeballing, which is a loose, right, value of 63%. So there is a standard deviation of about 3. Okay, so I am going to cut it off. I'm going to run only 60 hours. That's a better management. So you will be, okay, preventing the risk of equipment failing at 63 hours if you ran like 65 hours. Okay, so if you ran 65 hours, you would have encountered, okay, chance of failure at 63 hours of operation. So therefore, if you're a better management, I'm going to cut it off at 60 hours of operation, okay, and perform the preventive maintenance program every 60 hours of operation. Okay, so that's preventive is nothing but you go and check the system and then you replace anything that that worn out, okay, with a new equipment components, yeah, so that your system is going to keep on going without failing. So anyway, that's the way we make the decision, yeah. All right, so let's get into mathematical analysis. Here is our very first function. So a little bit more complex than our simple equation. So here we're dealing with time. Okay, so every time we have a function, we're dealing with either time and you're looking at your system at a point of time. Yeah. So the failure probability density as a function again of time can be written as this. So you review your calculus and calculus 1, 2, and 3. Yeah. So ft equal to e to the power minus lambda times t. T is a little time. Lambda is your failure rate. Okay, review. And your e is just your for the exponent. Okay, e. And then you have a negative power right there. I'm gonna erase this. So now take a look at how we calculate reliability. Again, we're gonna use a function of time. So this is for a constant failure rate. So here this little failure rate is constant. So this RT is the expected reliability at time, again T, for the constant failure rate, okay, lambda. So here RT is equal to e to the power minus lambda and then T, okay. So now, the first question students usually ask me is, why are you using the same equation? So pay attention. See, look at that. And look at this. The same equation, e to the power minus, okay, failure rate times t. E to the power minus failure rate times t, okay. Why is it happening? Because it's the same system. And they are complement to each other, okay. And remember your reliability and the failure, okay. Your R and then plus F is 1, always 1, okay. Now we're dealing with the rate at the time t. okay, we will use the same, okay, calculus, which is your function, the same function. It doesn't change. So now let's take a look at the example to see it clearly. So here we have system reliability. Your system is gonna fail, all right, at mean time between failure. And we're gonna maintain the system by running or operating less than this time. Okay, so system reliability at time t is equal to 1, beginning of the operation. So you have your reliability R, and your time is at 1. It can be second, time, hour. In this case, let's just go with hour. So after 1 hour is equal to your E. The value of E is this, because don't forget, okay, your equation is like this. All right, time. So your time is 1 here, and your failure rate is constant, 0.015. Your E is 2.783. Okay, it's in your calculator. Excel, the same thing, to the power minus, and you put it in there and calculate it on Excel or a calculator, and you will get 0.9850. That's 98.50% reliability at t equal to 1. Yeah. System reliability. What about when we get to the failure time, which is the mean time before failure? 66.6 hours. We're using the same example. So when you calculate that, okay, this 66 is the hour. If you run your system all the way to the failure point, and you're gonna have only 36.78% reliability. Yeah. If you ran your system only 1 hour, look at that. Your system is 98.50% reliable fail. If you run and push your system all the way, okay, before or at the breaking point, your system is going to produce only 36.78 reliability, okay, meaning 1 minus this will fail. So we don't want to push the system all the way to this point. Yeah. So previously it was indicated that the probability of failure for an exponential distribution at MTBF is approximately 63.21. So that's the estimate, graphical estimate. So we know that R is equal to 1 minus your failure. Yeah. So therefore R is equal to 1 minus 0.6321 is going to give you 0.3678. Yeah, this is from the graphical estimate. So compare this and that. So this is from precise calculation, and you get about the same. Yeah, 0.36 up to 7. Yeah, it's pretty good. Okay, maintenance. So now we get reliability. So we're gonna assume 30% failure can be tolerated, okay, as an acceptable risk factor, because it's going to give you like a 70% system reliability. So we're going to assume constant failure rate is 0.015. Yeah, and we can calculate the time. So this time we're going to calculate operation time. Okay, what is a safe, all right, operation time that we should do if we want to keep the system reliable at 70%. So how many hours of operation are we going to do if we want the system to be running at 70% reliability? So we put that, okay, into here, 70%. In our calculation, you're not going to use percentage. You're going to use a decimal. So you're going to translate 70% to 0.70 to do the calculation. Is equal to e to the power minus lambda is 0.05 times t. Okay, and we are looking for the safe operation hour to maintain 70% reliability. That's a pretty good. So 0.70 we're going to get rid of E right there. Every time you put down the power and get rid of E, we're going to bring in natural log, which is ln. So you write find natural log for 0.70 on this side. This is just a mathematical review. Get rid of, eliminate your E right there, okay? And then you put down the power. So now we get ln 0.70 is equal to minus 0.015 times t. So now we will get, so this is calculus, okay? And this is getting into algebra. So now we want to get this. So therefore you want to, okay, move minus 0.015 to this side. So you find the log 0.70 natural log. So ln is a natural log 0.70 divided by minus 0.015. And you will get 23.78 hours. Okay, that's a safe hours of operation. If you want to keep 70% reliability, you will run your system operation about 23 hours. Okay, you can go to 24, but I would just keep it at 23. And then you check your system. So that's how we do maintenance for the system. Okay, first we pick the reliability, and this is going to come from the engineer, the executive owner, okay, because they have to pay millions and millions of dollars depending on your business size for the equipment. So they're going to tell you, hey, you know, like just keep 70. Most of the American manufacturing company has only about like 60 to, some of them have only like 40% reliability, okay, because we don't want to break the system. So this hour is so important, and this is how you calculate. Yeah. So here is your review for your calculus. So if you have an E power equal to a value and you want to find this, you get rid of that. Every time you get rid of E, you're going to call the natural log. Yeah. So practice that. Okay. So I have my time. That's a 23.78 hours. Going with 70% reliability. So your failure is less than 30%. Yeah. Okay. I'm going to erase that. I want you to study this because you will have to do this in your midterm. Alright, next one. Alright, now we're going to take a look at risk level. And risk level got to be acceptable for a system, right? That's why we use the term acceptable risk level. And we usually do this in preventive maintenance. You know, we're going to maintain the system. So here is the first example. And here I'm looking at assumption, and the failure cost is $7,500, okay, for each failure. So we have a preventive maintenance program, and we pay $250 for each routine, schedule routine, okay, to keep this preventive maintenance. It's nothing but you check your system, and it's going to cost you $250 per time. But if your system fails, you have to pay $7,500 to fix it. Okay. So equipment is operated 260 work days. Okay. And we're operating that equipment every day, 16 hours. Yeah. And every year we're using and operating this equipment 4,160 hours. Okay. That's a lot of operation, okay, for this equipment. So now we're going to calculate cost. So if you don't do maintenance, the equipment is going to fail because it's worn out, yeah, running that much. So let's calculate when is it going to fail. So you have a total hour 4,160 hours, okay, and divided by 66. Yeah, so that's the time, operation time, okay, at failure. So that's the mean time between failure. So 66 hours the equipment will fail. We are running 4,160 hours a year. So how many times the equipment will fail without maintaining it? It will fail 63,103 times within a year. So you will have to, okay, pay $7,500 to fix every time this system fails. So therefore, you have to pay 63 times. All right, $7,500. That's a $472,725 dollars a year you have to pay to keep or repair that system if you don't do preventive maintenance program. Okay, so that's a lot of money. Yeah. Okay, so let's go there. The acceptable risk level and preventive continue. Now, you're going to run the preventive maintenance program, and that would allow for 20% failure. So that's your mean time before failure is 16 hours. Okay, so 20% failure, that's 80% reliability, is going to require 4,160 hours divided by 16 times, okay, equal to 260 preventive maintenance that you're going to run a year. So one time that you run, you're going to pay $250. 260 preventive maintenance routine that you're going to do in a year, it costs you only $65,000. And you have only 20% failure. 20% failures is only running your operation 16 hours and then you check. Okay, we don't run all the way to 66. We're going to run 16 hours with 20% failure, 80% reliability. And how do you get this one? You already know they reciprocate. Yeah, so 1 divided by 16 is going to give you lambda. Okay, and if you want to get mean time before failure, then you do reciprocate your lambda. So if you do the regular maintenance by running the preventive maintenance for 260 times a year, you will be spending only $65,000 and your system will be running with 20% failure rate. Okay, so for 20% failure probability, equipment is expected to fail only 52 times a year. So 260 times 0.20 is equal to 52 times. So 52 times $7,500, it will cost you $390,000 per year. Okay, if you didn't do the preventive maintenance routine and let the system run at 20% and fix it only when it fails, it will cost you $390,000 because every time the system fails, you have to pay $7,500. But this, won't happen. Usually 52 times failure, they don't happen because your chances is only 20%, fail. And we usually do the maintenance, so therefore the system won't fail. So you will be spending, between 65,000 and 100,000 per year. And this is just a calculation, So the maximum, if you calculate the predicted total cost, if these things happened, it's $455,000 per year, which is less than, okay, not running the preventive maintenance program at all. Okay, so you can see the range. The cost range is going to be $65,000 to $455,000 maximum. Okay, but this usually don't happen. The system don't go 52 times because we never get to 16 hours, right, of operation time, because the preventive maintenance activity always check and replace any kind of worn out or risky part of that system. So you will be spending around here most of the time. Okay, this is just the worst case scenario. If it happened, then you would spend this much, but it usually did not happen, so therefore you would never spend this much at all. Okay, this is just a calculation. It's a predicted maintenance to come up with a great preventive maintenance routine. Anyway, so now you know how to calculate the time the component or the equipment can fail, how to estimate the failure percentage, how to estimate the reliability percentage, how to maintain the system before it breaks, and then you know how to calculate how much it is going to cost for running the regular maintenance, and how much it's going to cost by not doing any kind of maintenance and let the operation keep going until it breaks. Okay, so preventive maintenance, running it is usually going to save you incredible amount of money. Alright, so the last one is a conclusion. So in this scenario, in this problem, the preventive maintenance option offers a saving of $472,725 minus $455,000. So this is the maximum, okay, with the worst case scenario. Will give you a saving of $17,725, okay, dollars. Usually is way less than this, because the failure usually do not happen if you run the preventive maintenance and keep the system running. Okay, so therefore you will be saving $17,725 and more all the way. Okay, but again, prediction, we always have to predict minimum, okay, minimum, the least it can happen, and all the way to maximum, the most, the worst case scenario. You always have to come up with the worst case scenario and the best case scenario, and you're going to keep your system always around there. The best management is going to keep the system around here. Average is in the middle. Worst is going to be around here. So if the management is cheating the money, okay, from the company, you're going to see they're going to maintain the system, but they're going to charge you within that, or maybe to the maximum. The company executive, okay, got to use even FBI or CIA for international, okay, businesses. This money, cheating money, there's a lot of money, and the people cannot monitor the work of another individual 24/7. Okay, so if you want to do the bad things, you do bad things around here, and usually management do that. Cheating money, stealing money is called a corporate crime. Usually is cheating money, like nicking the money out of the company, because they are educated. they know this. Okay, they also know how to maintain the system, and then change the records in the system. So reports, are lies. FBI for the domestic company, okay? CIA for the international company. They go over these accounts, reports, records, okay? And work with these accountants, auditors to see these numbers. And usually the crimes are not individual. Usually the crimes are organizational. So everybody do it in that group. So that unless somebody break the loyalty, that case will come up. Okay? And if you're all in it together, then you have all kinds of, money shared among people in that organization or group. Okay? So anyway, those are the corporate crime usually handled by the two agencies. Government also involved in it. And when it comes to big money, yeah. But majority of us will never go beyond average routine work. So anyway, I have to teach you, because we don't know like where you're gonna work. Sometimes if you're lucky, then you go get into real big corporations, and you have to be careful of who you are working with. Okay, it's up to you. If you want to go into the money direction and you're okay with that and you feel safe, do it. But for university, we always teach our students to be the best. Okay, so the best always come with the right attitude and integrity. And it's better not to do these things. But again, it's your life and it's up to you. Okay. So you have a freedom of choices in your life, and also you have a responsibility to take the consequences of your decisions. So anyway, so I'm gonna stop right here, and we're gonna move on to the second part.